Okay. So, hi everyone. Welcome to our monthly public talk series of IEEE Women in Engineering Affinity Group Albuquerque section. I am Aisha. I'm the chair of IEEE Women in Engineering Affinity Group Albuquerque section. Today, Dr. Antonia Papandreou-Suppappola, a professor in the Department of Electrical Engineering at Arizona State University, is joining us as our keynote speaker. She received her PhD in electrical engineering from the University of Rhode Island in 1995, and she joined the School of Electrical, Computer, and Energy Engineering at Arizona State University as an assistant professor in 1999 and was promoted to full professor in 2008. Her research interests are in the area of statistical and time-varying signal processing and contributions in radar wireless communications, biomedical and genomic signal processing, and structural health monitoring. Her publication records include 3 books and more than 250 journal articles, conference papers, and book chapters. She was elected fellow of the IEEE in 2013. I'm going to let Professor Papandreou talk about her graduate students and her lab herself. But before that, I would like to ask Dr. Suppappola to say some words before we start today's talk.
Thank you, Aisha. Thank you for the kind introduction that you made for our speaker today. So a few words about our affinity group. So we are a relatively small, not that new at this point, IEEE Women in Engineering Affinity Group. It is a great pleasure to have Antonia today with us and to give some background information about this IEEE Women in Engineering group. So the main idea of our affinity group is to bring together students who can be inspired by faculty or professionals in the industry that have a stellar career and have gone through different difficulties, I should say, in their path, so they can inspire our young students and young professionals. And we couldn't think of a better speaker than Antonia. So some personal background information, how I know her. So it was relatively recently that we met in a talk that I gave at ASU. So it was a great pleasure to meet her, and she hosted my talk. So I was really, I felt very friendly and familiar with her. So even if I didn't know her for a long time, so I think that this can be very helpful for our students. So without taking more time from you, Antonia, the floor is yours.
Sure. Thank you, Aisha, and thank you, Rini, very much for inviting me and hosting this event. I'm really excited to do this. So I will just jump straight to the talk here. I tried to find a catchy title, as you know, we always want to have the right title to attract attention. But since I wanted to talk about women engineering as well as my own research, I use the word time-varying environments, and I will demonstrate. So sensing to information in time-varying environments. So 1 second here. Okay then. I am not used to using this mouse. I'm sorry. I should have practiced before. Oi. All right. I thought I could just click this, but I guess it doesn't work if I just, maybe if I hit enter. All right. There we go. Instead of starting by introducing myself, Aisha gave a good introduction there. I'll talk a little bit about myself towards the end, so I don't get carried away and talk a lot. So anyways, so I'm going to touch 3 areas. One, women in engineering. And I graduated with my PhD in 1995. I did my undergraduate in the US, so I came to the US in 1985. So I have seen changes, and I'll talk a little bit about that. I've also seen large changes the last 30-something years in technology. I mean, things are moving much faster than they did before. as in academia, as Irene most probably knows, really have to move in that pace. We need to bring funding. That's part of the requirements. I love teaching, but I also love research. So we have to move along at that speed. So I will talk a little bit about that as well. And then just a tiny little bit about my research. I decided not to give too much information. I'll be happy to give additional, anyone that wants to know more about it, I'll be happy to do so. Okay, I'm doing it. Enter. Okay. So I looked up some things. The earliest data that I could find was from, let's see, move this from 2021. I sometimes I'm surprised that, so when I was a student, an undergraduate, there weren't that many women. And there's been a lot of activity to encourage women in engineering through the years. And I've seen an increase, but lately the increase is not that substantial. So I'm surprised to see such a low number of female students in my classes. So I just so since my PhD, so we definitely, the first row here is definitely undergraduate. It's definitely increased, by a good percentage. This, the data kind of jumped in between. So I don't know what's in between there, but noticing the master's and the PhD, yes, there's definitely an increase, but towards, this last 10 years, okay, and it's a good number of 10 years, there was not much of a change. There is a change, but not as much as we would like to. So then I looked into women in engineering workforce. So this is something that I've been hearing a lot, that this problem of attrition, women leaving engineering after they start working. So the data that I found here, provide my source at the bottom. So years since graduation and the percentage of women working in the workforce, academia, labs, industry, it's all together, okay? So it has very good percentage the first 5 years after graduation, but there's this very sudden drop from the last, after 10 years after graduation. A lot of women stop working. And I'll talk a little bit about some of the reasons. And it turns out for specifically, so this is engineering in general, but specifically for electrical, there's only about 9% actually employed in the electrical engineering workforce, which was a pretty small number as far as I'm concerned. So I looked, it's not easy to find studies to get actual reasons. Some of the things that I agreed with, I gave some of the links again. So a lot of the reasons was lack of representation, not given the opportunities to, or even have access to leadership opportunities. Some change the career interest. There's a lot of the reasons were family related, but there was also lack of promotion or increase of pay, okay? So as of now, this was 2021, over 40% of highly skilled women who enter the field of engineering leave by mid-career, okay? So I think there's a big problem as far as retaining us working in industry or in academia, or so I have found that this is an even a bigger problem that I think it's important to address it. So I found this information on this was on the SWE website. So it talks about workforce sentiment. Women who leave engineering have lower levels of satisfaction and commitment than women who stay. I like the second point. Additionally, managerial support for work-family balance and professional development opportunities are essential for women to stay in engineering professions. So this is just some things I found, but it also looking at the overall. So as far as I'm concerned regarding myself, I am very much grateful for the support I received from my family, from my husband, from my sons. It wasn't easy to make some of the decisions I had to make. Definitely still promote more women to pursue engineering degrees. Senior women role models. It's important to discuss, approach people, other women, I guess. Here I am talking. How do we balance work, parental, and household responsibilities? Like I just said, but also form support groups, like meeting Irini, for example, a few weeks back. That was great. I hope she reaches out if she ever needs any help, and vice versa. But also get some, actually go ahead and make sure you do present your ideas. Don't let someone else present them for you. Collaborate with other women. Write proposals if you're in academia, or if you're engineering students, get together for projects and demonstrate what we can do. I think it's that's very important. Now, there's a lot of emphasis on entrepreneurship, but some women do start owning their own tech companies, and I think that's wonderful. That's another way to show that yes, we will persist being in engineering, and show that we have what it takes to continue working while still having some balance with our household as well. Now, I said at the last point, adapt to interdisciplinary challenges. Okay, so that's with all the increases in jumping from, not jumping, but moving fast from one particular area to the other. So this is my second point. I'll just talk a little bit about, I should have started, I need my time near me. So when I started in 1995, what I was working on was very theoretical. It was analyzing signals with these advanced transforms. You may be aware, for example, what I'm showing here in this figure. All right. My second area here is statistical signal processing. And I'm going to talk about some of these applications, but it has everything to do with dealing and processing signals in noise. Okay. So this is what I'm calling the path, my research path, as the technology went through this rapid advances. So 1995, when I graduated, it was this was my work. At the time, I remember after I was a postdoc for 4 years, then afterwards, I got started as an assistant professor. I wrote my proposal for NSF, for the career proposal. I was so excited. I knew all this work. And what came back is I did not receive it, my career, when I first, I shut my door when I received the news and spent some time in my office. But then I got some feedback. I took the chance to make appointments and go see some of the program managers. And that's important. They need to actually see us, and they cannot look at your proposal ahead of time, and they can't give you pointers towards that. But I brought my abstract and my summary, and they gave me some feedback. The main feedback is, right now, signal processing for wireless communications is what you need to do. So I had to spend a year learning more in wireless communications. And after I rewrote my proposal, I received my career award. So it's important to move with the times, I guess it's one way. So through the years, I've worked with radar tracking, and I still do a lot. So I was putting durations before, like from this year to this year, and then I figured, wait a minute, I still continue to do all this research. So waveform optimization for active sensing, structural health monitoring is finding defects on airplane wings, for example. I've applied, so in my mind, what I started with is some tools in signal processing, and now I can share it. I've done some work in genomics and so on. And I'm not going to talk about each one of them, but all the way to a current project that I have related to 6G, what it call future wireless. Oh, maybe I need to use the arrows there. Okay, so this was I was part of this lecture series from the Air Force Office of Scientific Research, where there was a few of us discussing signal processing people and people working on radar applications. And the idea was, okay, what is the role of artificial intelligence? I mean, so this is the time while everybody looks at machine learning applications. And if I were to try to write a proposal right now and did not mention machine learning and showed some initial results, irrespective of how good my proposal is, I know it wouldn't be funded, and I've experienced that throughout my career. By the way, I love this picture there. What am I looking at? There's so many challenges coming up. Of course, we don't know what's going to happen in 2040, but we can see that we're moving towards autonomy technology. We have weather extremes we have to deal with. There's a lot more activity. There's going to be, I found some things here. I found some interesting pictures as well on the web. There will be commercial space travel. Instead of going to North Carolina at the beach, we'll be heading somewhere else, and so on. But there is a harsh environment. For example, the video, the orbital debris is a big problem with all the pieces, anywhere from very small to very large pieces, for example, that break from satellites and so on. So that's something that we have to deal with. So what I put here is, again, I'm speaking more in a general. So before, a lot of my research was sense, as in get measurements, adapt, as in optimize resources, infer, make a decision. So now we include the learning part there. And the learning part is indeed, it's not just because it's what's good right now, but I've been doing that for the last 10 years, actually, where we do not always have the ideal environments. We cannot assume that, for example, the noise intensity doesn't change with time, or that I have all the information that I need. So we need to learn to adapt to new information in real time. Oops. Okay, so I call it decision theoretic learning. And there's an emphasis on cognitive systems, and that's also falls part of AI. For example, in radar, we'd like to have what we call fully adaptive system. So we optimize any resource from power usage to waveform, to sensor scheduling, and so on. And in order to increase the performance, autonomous, we want things to run by themselves while adapting to different changes. But this cognitive adaptation is still, there's a lot of challenges in it. There's still a lot of things missing. How do we have machines look into perception, reasoning at all levels? There's a lot of information. There's still a lot of work to be done. Something that I think is very important is, I know right now data science is what's big. Everybody wants to do data analysis, data processing with machine learning and learn from the data. And one of the reasons is because there's large amounts of data that we now have collected. However, we have all these mathematical models that we can't just ignore those and just use the data. Okay, those mathematical models were tested and explain behavior and help us to make predictions. However, we can also make sure we update those models if needed based on new information. Now, data-based, yes, we can learn a lot of information. However, we can't just collect all the data that's out there without any pre-processing. There's definitely a lot of noise, a lot of, and not only relevant information, but also is all this data necessary? Would have gotten the same information with half the data and less computational time. And then the last thing is what I call conceptual-based, tuition-based. Different people look at different, but it's the idea of including the human in the loop. It doesn't mean that we have to let artificial intelligence do everything. We can still provide and talk a little bit about accounting for ethical concerns. Sometimes the correct decision based on the facts that machine was given, for example, would be something that has ethical concerns. So that's where human intervention would be important. So I gave an example here. This was part of I give that as an example of my talk. This has to do with deep brain stimulations. So patients with Parkinson's disease, after medication stops working for them, they have this stimulation on the brain to help them, for example, stop with the shaking of their hands and so on. So this, I just did a timeline again, how it started as early as 1947. It was all external before. Then it was done internally. But the whole point is to come up with a deep brain stimulation that's goes in our brain, and we don't have to go to the doctor to upgrade, to change the settings, but it's a closed loop. The last data that I had at the time, that was a year ago, was machine learning being used to make it specific to a patient. I'm going to have to move a little bit faster. So what I have here is, this is still the same timeline. Now, it just happened that on Friday, I went to this workshop. It was trying to interact with BNI's, Barrows Neurological Institute, half an hour from ASU. And we want to increase the collaboration. So the dean's office set this up. So over there happened to be this doctor, right, from Medtronic. And he gave half an hour talk on the same problem. And he mentioned this brain sets. So this is a new, as of 2023, something that Medtronic is using to make it even more personalized and adaptive in real time. So things are happening. So what happens by 2040? I guess I still wanted to include that. Yes, non-invasive DBS, but is there a way that we can keep all the we can keep in our memory everything we've learned? As we get older, some of us tend to forget a lot of things, so could there be some implants to help us remember? But then there's also issues of privacy and so on. So everything comes with keeping in mind the human aspect. So I'm jumping to something more specific. That's something, this research, I've been doing this type of research for the last 20 years. And this has to do with looking at dynamic, some of you may recognize this from control theory, but it's the idea that I have a parameter here, x of k, that I need to estimate as it changes with time. This is normally called the hidden state, because we cannot directly obtain information from it. So we use these two models here. We have a physics-based motion model, and I gave an example, very simple example, how you can get the current x coordinate using the previous and the previous velocity estimate. So using this transition state equation and using the measurements that we've extracted, using those two equations, the question is, can we find an estimate of the states? And there's a lot of work that has been done in this area. This is nothing new. You may have talked about, so this is called Bayesian filtering, Kalman filter, extended Kalman filter. The last 20-something years, particle filtering became very important. I just have a little picture of the particle filtering. In all these cases, we have an iterative algorithm. We assume some initial conditions. We use a prediction to predict and estimate, then we use the measurements to update it. And this is almost, it looks like sampling, but it's set up to use the prior probability, the prior PDF, and the measurements to help us estimate. Now, it's a lot of work that can be discussed on this, but the idea is the number of particles has to be very, very large in order to be able to get a good estimation. So, so what I showed you before, what I showed here, I guess, is what would be done if I had, go back one more. There we go. So this would be able to track, for example, a single target in node conditions, meaning we know the models, we know the noise, but things are changing at a fast pace. It's not just one target that we're after. There's situations of high noise. Here is a case where a radar signal, that's what we call a linear chirp, or a signal whose frequency content increases with time. And what you see here, a case where the noise we can easily detect. We can see that there is a presence of a signal, so we can extract the information we need. But then we see what happens when there's high noise. But there's a lot more. There's could be clutter. Those are reflections from other objects in the scene. Interferes, it could be a friendly or it could be an unfriendly interference with our communication. Sharing spectrum, this is a big thing now. Spectrum is there's so much spectrum that can be used. So there's a lot of there's a need for spectrum. So this is in 5G, we have what's called sharing spectrum between wireless communications and other wireless systems. So here I just showed the same type of time frequency. You see this linear, the line here, but all these other things are frequencies, single frequencies for multiple communications, for example. So how do we deal with that situation? This situation is, we're looking at a scene, but there's multiple targets that come and go. So how do I know that I am following the correct one? The weather can change suddenly. I cannot assume that I know the covariance of the measurement noise because I estimated ahead of time. If things change suddenly, I have to keep up with that. And space. I've mentioned a lot of the difficulties of the space, and of course I had to show my diagram. This was, I put it on top of the earth there. I thought it was kind of cool. At any rate, so a little bit of the work that I've done towards this very general, looking at the time, designing waveform optimization was a work that I've done in the past, where we actually predict what the cost, what the error will be in our estimation, one step ahead of time or multiple steps ahead of time. And based on that, we select a waveform. I'm not going to go into the details, but this is where we adapt. We whatever we have up to that point, we use to see if we can predict what's the best scenario of our resources to use. Then the problem becomes a lot more complicated. For example, we could have an unknown number of targets that changes with time. The targets are unlabeled. What does this mean? It means that I don't know that this target is target 1. So when I transition to the next time step, how do I know I didn't use the X coordinate, for example, of another target? So there's a lot of dependencies, and those are statistical dependencies. So they need to be addressed. There's multiple sensor measurements. How do we know which measurement goes to which target? Measurements can include clutter and so on. So here, we not only have to estimate position and velocity from the XY coordinates, but we need to determine the label of the target, how many targets are present at any different time, and this association. I'm not going to go into details, just a big picture. There's a lot of talk about Bayesian non-parametric modeling for inference. Inference is, I guess, another way to decision-making, extract information. So this part of machine learning of using the data is that we can have, so if I look at this equation here, for example, say, I don't know the probability density function of, I guess I should have used the measurements, it would make more sense here, but some information, some data x of k that varies with time. And how do I estimate? So we use probabilistic modeling. We're going to use some parameter distribution, and we're going to model the parameters of that distribution using what we call conjugate priors. And then we're going to use that in prediction. So in what I have here is introducing this value, this parameter theta that came from out of one distribution, right? A is going to be the hyperparameter that we're going to use to learn theta, right? Because the learning has to relate, we have to, these theta parameters have to be related. They have to have an intuitive relationship to the information we have to our data. So the way we use Bayesian, so we see here that this is the, we can use this PDF of A, this hyperparameter A. And the idea of conjugate priors is that both the prior as well as the distribution of the hyperparameters, given the parameters we're modeling, if they belong to the same distribution, family of distribution. So there's tables of specific distributions and their conjugate priors. So for example, if I don't know the mean and covariance, second there. If I don't know the mean and covariance, then we can estimate them using the inverse normal Wisher distribution as the conjugate prior. So this Dirichlet process, and I guess I didn't emphasize that at all here, about these parameters, about this theta, where do they come from? So there's a lot of models use parametric, such as Gaussian, versus using other processes, such as what we call the Dirichlet process, that allows for infinite number of parameters. And that's important because then as new data comes in, then we don't have to start from all over again. So very little about Dirichlet process. They call it a distribution of distributions. It's a discrete representation, depends on these two parameters. These parameters, theta sub I, they're such that an important property is that, say we've collected the first I-1 parameters, and we determine each one of them has its own label, the label being the theta. So when I look at the next parameter, there's only two possibilities. It could already be existing in one of these other clusters, right? Because there's a chance, this is the probability of getting a value that I've already received, I've already collected, versus a new draw. So we use this in our case to label the targets. We use the thetas as clustering parameters that provide information associated with each target. Again, there's a lot of detail. This is just one. I just wanted to give one example. So this is another method. This is a case where we have 10 targets. This is X and Y coordinates. These are the true tracks of the motion there. Cardinality is the number of targets, and you can see the true one and our approximation. This is another state-of-the-art algorithm that used random finite sets. That was the state-of-the-art for many years, but using the Dirichlet process for the labeling, it makes a big difference. Okay, and this is one of the later things, and I'm not going to talk a lot about it, but suppose in addition to all of this, here's my measurement noise, the intensity changes, right? It's not a longer, just a, if it's Gaussian, I don't know, the covariance change with time. So what I just gave that as an example, our problem becomes more complicated. We have to model the parameter for each target. We have to associate it to a measurement, and we also have to model and relate all that with a different DP process for the noise intensity. So these problems, this is some more specifics about the dependence. I will not cover that. So with that, I finished the, like I said, a very overall, and I'm looking at my time. I have 2 minutes before I get questions asked. So this is what I meant to say at the beginning, but I just wanted to mention that I am from Cyprus. I came to the US let's see. Oh yeah, I gave you my age. I haven't turned 58 yet. I'm 57. I have 2 sons. These are my 2 boys in North Carolina from a couple of weeks ago. A 26-year-old and my 19-year-old, Solos and Stavros. Regarding my, I started electrical engineering in 1985. At the time when I came here, I just wanted to do math, and somebody suggested, well, there's a lot of math in electrical engineering. So that's how the choice happened at the time. But I also wanted to point out this person, my advisor, my mentor. She's wonderful. I will never forget everything she has done for me. She's one of those mentors, senior, that can help us with what she went through. I can't believe that I'm a senior as well now. So what I went through, she just actually retired. I couldn't believe she could retire a couple of years ago. But at any rate, she made a big difference in my life. And I believe a lot of the success that I have I owe it to her. She's just amazing. I was going to show you a picture of my wedding because her little girl was a flower girl, but I figured, let's not go. Anyways, but I wanted to show a few pictures of my students. There's a lot of them missing. I never sat down to collect all different photos. So any of my students that graduated that are not here is because I couldn't find photos on time. But I don't try to graduate too many students. I prefer to connect with my students. I think that's very important. As Irini will mention, that being able to talk to your advisor and discuss any issues, especially for women, but men as well, of course, it's very important to connect. So spending time. These are some of the funding I've had through the years, but but also I kept getting distracted by me and how different I looked through the years. Oh well. And oops, almost done it. One more. Okay. And these are some more SPAS kits. Again, these are current PhD students, Abigail and JC. This is Ying Li. She graduated, my goodness, I don't know, 12 something years ago, but I'm showing this picture because she got married at my house. So we had, she was away from home, and we just, of course we didn't have a big wedding, we went to, I was present at the judge office, and but then we came to my house and we had lots of fun. So this is my last slide. And again, thank you for this opportunity. I get very excited to see them. I have to go afterwards. I have to spend time finding everybody's photos. And then there's one of my PhD graduates who's at the University of New Mexico because I have to show Steve So at any rate, again, thank you, and I'll be happy to answer questions.
Thank you so much, Dr. Papandreou. So let's start with the questions. I could actually start. However, I haven't been able to track which slide it was, but I think you will be able to still understand my question. So you were introducing interferers and then clutter signals earlier. So I wanted to ask you how these interferer and the clutter signals are handled or mitigated when we're performing real-time tracking. And I believe it's going to contribute to the complexity. So how is this complexity going to affect the real-time tracking?
Yes, it's a very good question. It definitely makes a big, oops, there it is. A big difference, especially, I mentioned enemy, but there's a lot of work right now this last few years on adversarial wireless applications, meaning the enemy has, I guess I shouldn't be using the word enemy, but they have, they learn our intelligence and then they build their own higher intelligence, and then we have to figure out that intelligence. So interference and clutter is a big thing. So one of the good things, it is another thing that we have to take into consideration, but especially with this non-parametric modeling, we're looking for signals that have a structure, whereas clutter is very random. There's different models. I mean, people have studied different models for clutter, but if we're clustering signals, then and we have tried that actually, the example with the 10 targets, we had a situation with clutter in it, and it got clustered by itself separately. Now, it doesn't mean that it removes it completely, of course. So there's still lots of work going on. I have a master's student who's working on a clutter tracking application right now. So still a lot of work to be done. Thanks, Aisha.
Thank you so much.
Sure. I see another Greek name there. I was excited. Stavrula, hi.
Hello, Antonia. This is not quite my area. I'm a photonics researcher, but nowadays people are interested in materials that their permittivity response changes with time. So I was interested to hear a little bit of your research, because when that happens, the signal can change in frequency. So how you monitor the output signal when it changes in frequency, what you're doing could be relevant to that field as well, I think.
So if I had a little bit of a hard time following, I'm sorry, but you mentioned inconsistencies in the data.
There are new materials nowadays. They're trying to change material properties. So
material properties, yes.
Yes, so that their permittivity response changes in time.
That's right.
And when that happens, your input signal will not keep its frequency. As it propagates, it can change frequency. So I think what you're doing in your time-varying environment to analyze the signal and the frequencies it corresponds to could be relevant to that field as well. So
yeah, I think so. I think so.
So please to learn a little bit more about that field that you're doing.
Yeah. See, we could collaborate.
Sure.
I love multidisciplinary work. That's something I told Irene before. There's a lot of people here at SU. There's a lot of different areas. I've collaborated with people from genomics, from biomedical, mechanical engineers. There's all a wonderful problem. Now, it could be my area, signal processing. I see hands up. So I see Sean. I don't know who had first. Tigderis, is that another Greek name?
Yeah. Yes, you got it. My question for you isn't necessarily retaining towards the presentation. It's more of a personal question. I was going to ask, since I'm new to the field of research, since it's my first year currently working within research, I was going to ask you for like what would you say is your most challenging obstacle in your research career so far? And how did you overcome it? Because I'm finding myself in a situation where I'm researching a lot of things that I've never done before, and everything is starting to feel like an obstacle. But I just wanted to ask if, like, what was one instance
Sure,
that
that's a
you
good
overcome?
question too. So it's very important to keep, being able to express yourself, being able to tell your advisor, this is very hard for me. I have not, I need more time to spend learning this. As the advisor can, ask the advisor, do we have some additional literature for me? I mean, yes, we want the students to go out and search and find information. But if you're not seen it before, it could take a lot more time. Now, knowing from my funding, my situation, PhD students get paid. That's why we need to go and get funding. And I have certain problems I need to work with. So there's not really a lot of freedom to tell the student, yeah, you can choose whatever you want and I'll work with you. So yeah, we do guide students in a specific direction, but it's important to allow the student more time if needed, and definitely understanding of what's going on.
Yeah, I see. Because in your presentation, you were talking about the sort of how you're connected with your students, and even like continuing, like you had a wedding at your house.
Yes,
So
I had two weddings. I only showed one of the pictures.
Okay, so 2 weddings. See, so I'm seeing it's more of a connection with the advisor.
I get excited. As you can see, I get very excited. But I teach like that in class too. And I've seen Irini talk during her presentation. So she's like that too, except she's louder than me. So I don't know if it's a Greek thing. I don't know. But I get excited. And I think that's, it doesn't mean your advisor has to be excited all the time. It doesn't mean like that either. But they, it's important that they stop and listen to you, and they respect you the same way you respect them. Let's see.
That's a good input, Son. You need to find a wife, and I need to buy a house in order to do what Antonia did.
Well,
okay.
To have
we
the weddings, I mean, you can have a lot less people. Oh my goodness. I try to provide the right food too. Of course, I wasn't going to cook it. I had it on a place and had it. But it was exciting. I mean, come on, who would have thought, as part of my duties as the advisor, that I have to schedule, handle weddings. Now, I don't try to put people together. Oh, another situation, two of my PhD students got married to each other before they finished. So a lot of nice things happen.
Yeah. Okay. Well, thank you for answering.
No problem. And I guess, I don't know if I can say Sadmian. Is that how you say your name? I'm sorry.
Yeah, Professor. So I had a technical question. So I think my research has been mostly on positioning, navigation, and timing, PNT systems, and alternative versions of it. So I was wondering, since you're focusing on real-time tracking of objects in time-varying environments. So what kind of data sets are you using for model training in general, and where to find such data sets?
Yeah, so that's one of the things. I don't work specifically with real data. We simulate a lot. In some aspects, sometimes we give our algorithms. For example, we give our algorithm to the Air Force Research Lab, and they use them with some real data. But I don't often work with real data. We simulate the situations as much as we can. When it comes to real data itself, it's obviously everything changes. I mean, it's there is I was listening to a presentation not that long ago where they talked about how long it takes for an academic algorithm that a PhD student came up with and published. How long does it take before it actually being used? It takes a long time, and that's part, I guess, of the entrepreneurship, trying to get the methods out there. So there are some databases out there. We don't use them, but collaborating with people, from research labs, that's a good way to get data. So.
Thank you, Professor.
Question, you're welcome. I don't know how I'm gonna try. Sorry, I'm not gonna try. You tell me your name.
I think my name is Adi Damola, but Damola is fine.
Wow, that's a very yes.
Yeah, so my question is just, I mean, a little bit general. So what are the current limitations of your research and how do you plan to address them in your future work? And
Yeah.
as an extension of that question, I also want to know, are there any exciting extensions of your work that you're really excited about? So.
Sure. So this last new project that I'm working on, I'm part of 7 other collaborators. So they actually we put a center together, Center of Future G. So we're supposed to study 6G and above. Definitely not 5G. They don't want to see 5G, 6G and above. So so reinforcement learning is another area that has a lot of potentials. So of course, I have student that's been, took a class on reinforcement learning and is now working towards, how do we do waveform design? That there's, you don't have to, there's a lot that you can do. You don't have to train ahead of, it depends how you use it. So that's one new exciting area. Now, of course, what I didn't mention is every time something new, I have to learn it too. So there's just so much time in the day, but so that's one direction that we're definitely heading. So
Okay, so any other questions? If not, we will have to close for today as we are over the time. And I guess some of the students also have classes. But thank you so much. Thank you so much. It was an amazing talk, and I think we've learned a lot from you.
Yeah, I hope you learn about the clicking. That let's not do that. No, I really appreciate. I enjoy this, and I think you've done great work. And getting to me, we get busy, and your reminders were extremely helpful. So I think this was a great experience for me as well.
Yeah, we appreciate your participation, your time. Thank you so much. And yeah, so let's close up. Good night, everyone. I will be uploading the video very soon, and I will email you. Thank you so much once again.
Thank you so much,
Bye.
Antonia.
Bye-bye.